Good morning, everybody. Last time we had seen the chemical equilibrium, we had seen the examples, and therefore we had drawn a graph for the reactant coordinates, that is the how the reactant when it reacts, the graph for the reactant and the product we had drawn, and therefore we had seen the chemical equilibrium. We have seen that the chemical equilibrium is dynamic and it is not static. What it means? It means that at equilibrium, the reaction actually practically doesn't stop. The reaction is still going on, but at the equilibrium, the rate of the forward reaction and rate of the backward reaction becomes equal. Therefore, the reaction hasn't stopped, but the concentration of the reactant and the product, the ratio of the concentration of the product to reactant, it remains constant. Hence we say that the chemical equilibrium is dynamic and it is not static. Then we had seen the law of mass action, law of chemical equilibrium, and from the law of chemical equilibrium we had derived the equation for the equilibrium constant. The equilibrium constant, which is equal to the rate constant for the backward reaction divided by the rate constant for the forward reaction. So this is how we had derived the equation for the equilibrium constant. Now the next is the type of equilibria. The types of equilibria. The first is homogeneous equilibria. The homogeneous equilibria is nothing but when in the reaction all the reactant and the product, when they all are in the same phase, such equilibrium in the reaction is called as the homogeneous equilibrium. The example of this is the hydrolysis of crystal. This is methyl acetate, which on a hydrolysis gives acetic acid plus alcohol. Here all the reactants, they are in a liquid phase, hence this is the example of the homogeneous equilibrium reaction. This homogeneous equilibrium reaction, actually here as the equilibrium is formed, that means here the arrow it must be a double arrow. So this is what is the example of homogeneous equilibrium. The another example of this is the formation of ammonia from nitrogen and hydrogen. These all are in a gaseous form. This is also the example of the homogeneous equilibrium. The equilibrium formed in this reaction, in the formation of ammonia, the equilibrium formed in this reaction is a homogeneous equilibrium. Now what is heterogeneous equilibrium? Obviously when the reactant and the product, when they are not in a same phase, therefore that type of equilibria formed in the reaction is called as the heterogeneous equilibria. The example of heterogeneous equilibria are the decomposition of sodium bicarbonate, which gives, this is actually in a solid form, which gives sodium carbonate plus carbon dioxide plus water. This is the example of heterogeneous equilibria, where these are in a solid while the other products are in a gaseous phase. So this is the example of the equilibrium formed in this reaction is a heterogeneous equilibrium. The decomposition of calcium carbonate this is also the example of the heterogeneous equilibrium. Here these two are in a solid while this the product is in a one of the product is in a gaseous phase. So therefore the equilibrium is established in such a reaction where at the equilibrium when all the reactants and the product when they are not in a same phase or when they are in a different phase, that type of equilibria found in the reaction are called as the heterogeneous equilibria. Now let's go further. That is the perfect gas equilibria. Perfect gas equilibria. That means actually when the reactant and the product, when they are gaseous, and in the gaseous reaction the gas which are present there, when they are the ideal gases, and in such gaseous reaction the equilibrium form that we are going to see. We are consider a very simple reaction. A representative example we are considering. This is what is the simple reaction. A gaseous reactant A is converting into a gaseous product B. Therefore, for such reaction, if we want to write the change in the free energy in this reaction, therefore we can write this as the change in the free energy for this reaction is equal to, this is what is the equation which we can write to calculate the change in the free energy. Therefore, the delta G is nothing but change in the free energy in this reaction. Gb and Ga, these are the gift free energies of the B and A. Therefore, if we consider that these A and B, these are the perfect or the ideal gases. Therefore, the gift free energy of the reactant A is calculated as its standard gift free energy minus RT ln of PA, where this PA is nothing but the partial pressure of the reactant A and the equilibrium. So this is what is the gift free energy of the reactant. While similar formula we can write for the B, it's a standard free energy minus RT ln of PB. Now, from this equation or these values, these equations we are going to put here. Therefore, what the equation will become? Equation will become delta G is equal to, instead of Gb we are going to put this. So, G0B minus RT ln, sorry, this is plus RT ln PA minus Ga, that is minus, sorry, plus RT ln of PA. PA and PB, these are the partial pressure of the reactant A and B respectively at equilibrium. So therefore, delta G is equal to these standard free energies. Now, if you apply this negative sign inside, that means you multiply with this negative inside, so this will become negative as well as this will become negative. Therefore, G0B plus RT ln of PB minus G0 of A minus RT ln of PA. Now, what I am doing is, these two terms I am taking one by one. Minus G0 of A, because this is minus. So G0B minus G0A. The remaining terms are RT ln of PB minus, this is minus RT ln of PA. Now, this we can write as the standard free energy change in the reaction. Delta G 0 plus, now here we can take RT common, so inside the bracket ln of PB minus ln of PA. So delta G 0 the change or the difference in the standard free energy of product minus that of the reactant is change in the standard free energy. Like this. Here we have written the change in the free energy for the reaction is the free energy of the product minus free energy of the reactant. Similarly here, the standard free energy change of a reaction is standard free energy gives free energy of the product B minus the standard gives free energy of the reactant. So this is delta G0. Here we have taken RT common. So in the bracket ln PB minus ln of A, these are remaining. Now, according to the rule of a logarithm, here there is a subtraction of the PB and subtraction of the two logarithmic terms. So, according to the rule of logarithm, we can write them in a quotient. Delta G0 plus RT ln of PB divided by PA. This is what is the equation to calculate the change in a free energy for this perfect gas equilibrium reaction. Now therefore, this PV by PA, this is called as a reaction quotient. This is called as a reaction quotient. Which is denoted by capital Q. Now this reaction quotient Q is a very important value, or it is considered to be a very important in the reaction. This is actually like a equilibrium constant. See, for this reaction, if you write the equilibrium constant, it is nothing but the partial pressure of B divided by partial pressure of A. That means the reaction quotient and equilibrium, their formula are same, but they are not exactly same. They are not one and the same terms. These two are the different terms because the Q, reaction quotient, its value need not to be always equal to the equilibrium constant. Reaction quotient's value, Q value, need not to be always equal to the equilibrium constant value. That means the K and Q, these two are different. K is calculated when the reactant and the reactant gas molecule and the product gas molecule, they are at equilibrium. While the reaction quotient Q can be calculated at any instant of reaction. So therefore I am saying that the value of a Q is not always equal to the value of K, that means the equilibrium constant. But this Q, the reaction quotient, it actually predicts, or it is useful to decide whether the forward reaction is favorable for the equilibrium formation or backward reaction is favorable for the equilibrium reaction. So from the value of a Q, we can decide which reaction is favorable to attain the equilibrium, to reach towards the equilibrium. When Q is less than K, that means when the reaction quotient is less than the equilibrium constant, then therefore the forward reaction is greater. That means the forward reaction is taking place at greater rate to attain the equilibrium than the reverse or the backward reaction. When Q is less than K, that means the reaction quotient is less than equilibrium constant, then therefore the forward reaction is favorable to attain the equilibrium than the backward reaction. And when Q is greater than K, that means reaction quotient is greater than the equilibrium constant, then therefore the backward reaction is more favorable to attain the equilibrium than the forward reaction. So this is how the Q, reaction quotient, it makes us to decide which reaction is favorable for the equilibrium attainment. So this is what is the importance of the reaction quotient. Now, and the third, two possibilities we have seen, and the third possibility is when Q is equal to K. Q is equal to K means when the reaction is at equilibrium, therefore none of the reaction is favorable. The reaction stops. Stop in the sense the forward and the backward reaction attains the same rate, and therefore Q value and K value at that instant becomes exactly equal. Alright. Now we are going to see how to write the equilibrium constants for the reaction. Examples we are going to see. One example we will see the formation of ammonia by the Haber's process. This is the reaction. Now for this reaction, we are going to write the equilibrium constant. So how to write the equilibrium constant? Now when these are expressed in their concentrations, that means moles per liter, therefore their concentration, they are actually expressed in moles per liter, and the equilibrium constant K we can write this as, obviously, for the product raised to the power divided by the reactant. This is what is the equilibrium constant for this reaction, but here we have considered their concentrations in moles per liter, and their concentrations are divided by the standard concentration, that is 1 mole per liter. Therefore, see, if the concentration is somewhat moles per liter, it is divided by 1 mole per liter. So this unit gets cancelled, and whatever concentration is there, in this term the concentrations are expressed in the equilibrium constant इक्वेशन. हे जे काही कॉन्सन्ट्रेशन्स आहेत यांना एक्सप्रेस करताना जे काही कॉन्सन्ट्रेशन मोल्स पर लिटर मध्ये आहे त्याला काय करायचं, 1 मोल्स पर लिटर ने डिवाइड करायचं. त्याच्यामुळे हे कॉन्सन्ट्रेशन युनिट ते काय होऊन जातं, कॅन्सल, आणि फक्त तुमची युनिटलेस क्वांटिटी काहीतरी राहते. समजा 0.1 कॉन्सन्ट्रेशन आहे, तर हे कॉन्सन्ट्रेशन 0.1 झालं, आणि मग ते आपल्याला इथे सबस्टिट्यूट करता येईल. सो व्हाईल सबस्टिट्यूटिंग ऑल these concentration considerations, the concentration when they are considered in moles per liter, they are divided by 1 mole per liter. So unit gets cancelled and you get unitless concentration, which can be substituted here in the equation of equilibrium constant. So this is the equilibrium constant for this reaction when the concentrations are considered in a moles per liter. But as here all they are in a gaseous form, when they all are in a gaseous form, and instead of considering the concentration in moles per liter, if we consider them in terms of partial pressure, and this partial pressure they are divided by 1 bar, so again unit get cancelled and you get a unitless pressure. Therefore this is termed to be Kc, because here the concentrations are considered when the pressures of the gases are considered. Therefore this equation becomes partial pressure of ammonia bracket square divided by partial pressure of nitrogen into partial pressure of hydrogen raised to 3. So this is Kp. Why Kp? Because the pressures are taken. Partial pressure of these gases are taken. So when they are expressed in moles per liter, it is termed to be Kc. When the reactant they are considered in the gaseous form, therefore their partial pressures are considered. Here also, while considering their partial pressure, the pressure in a bar is there, whatever the pressure is, 2 bar is there. It is divided by a standard pressure of 1 bar. Your units get cancelled, and therefore a unitless quantity becomes 2, which can be substituted here. So this is how the equilibrium constant, whether the Kc or Kp, can be written for the reaction. So we are going to see more examples how to write the equilibrium constant for the reaction. A reaction is given: potassium chlorate, which decomposes to give KCl plus 3 by 2 oxygen. This is what is the reaction, and we have asked to write the equilibrium constant for the reaction. Now here, obviously, the instead of considering the concentrations, because here no liquids are there, the gases are there, so we can write it as Kp, which is equal to, now the concentration of KCl into pressure of partial pressure of oxygen raised to 3 by 2. This is in the 3 by 2 divided by concentration of potassium chlorate. Now this is the equilibrium constant for the reaction. Now when we see the law of equilibrium, we had said that these concentrations or the pressure whichever are we are substituting, they are substituted in terms of their activity, right? हे जे काही कॉन्सन्ट्रेशन्स आपण लिहितो किंवा प्रेशर लिहितो, या ऍक्च्युअली काय कन्सिडर केलेले असतात तर प्रॉडक्ट आणि रिएक्टंटच्या ऍक्टिव्हिटीज. मग ऍक्टिव्हिटीज म्हणजे काय आपण पाहिलं होतं की जेव्हा कॉन्सन्ट्रेशन मोल्स पर लिटर मध्ये असतील त्यांना 1 मोल पर लिटरनी डिवाइड करायचं आणि आलेली जी काही क्वांटिटी आहे ती त्या टिपिकल प्रॉडक्ट किंवा रिएक्टंट असेल त्याची ऍक्टिव्हिटी झाली, बरोबर. म्हणजे इथे आपण ऍक्टिव्हिटी सबस्टिट्यूट करतो आणि आपण ऍक्टिव्हिटीज ज्या काही आहेत त्या ऍक्टिव्हिटीजचे नियम पाहिले होते काही. त्याच्यासाठी आपण असं सांगितलं होतं की जर प्युअर लिक्विड किंवा प्युअर सॉलिड फॉर्म मध्ये जर तुमचे रिएक्शनचे रिएक्टंट किंवा प्रॉडक्ट असतील तर त्यांची ऍक्टिव्हिटी ऑलवेज 1 घेतली जाते. मग इथे पहा हे जे काही दोन, हे तुमचं प्रॉडक्ट आणि हा एक रिएक्टंट, हे दोन प्युअर सॉलिड फॉर्म मध्ये आहेत म्हणजे यांची ऍक्टिव्हिटी 1 घ्यावी लागेल. So therefore what your equation becomes for the equilibrium constant, it is only pressure of oxygen raised to 3 by 2, because the activity of these two are the pure solid and the activity of the pure solid or pure liquid is taken to be always 1, and therefore their activities are 1. If we substitute them 1, therefore our equilibrium constant Kp for this reaction becomes, it is equal to partial pressure of oxygen raised to 3 by 2. So this is only the equation for the equilibrium constant for this reaction. Let's see one more example. Calcium carbonate, which gives calcium carbide plus oxygen gives calcium carbonate plus CO2. Now this is solid, this is solid. Now this is what is the reaction. Now to balance the reaction, this is what is the reaction. Now we are going to write, obviously here also the gaseous reactants are predominant, so Kp we can write as Kp is equal to, now concentration of calcium carbonate. Now this is a solid, so we can take its partial pressure. This is a solid because. Now this is a gaseous, so we can write partial pressure of carbon dioxide raised to 2 divided by concentration of calcium carbide into partial pressure of oxygen raised to 5. Now again, these two are the pure solid. So their activity will be taken to be 1. So what our equation becomes? Kp is equal to pressure of carbon dioxide raised to 2 divided by pressure of oxygen raised to 5. So this is the equilibrium constant for this reaction. Next example. So this is what is the reaction. Obviously here all are in a gaseous form. Therefore Kp is equal to pressure of Hi, partial pressure of Hi raised to 2 divided by partial pressure of H2 into partial pressure of I. So this is what is Kp for this reaction. Now let's take one problem on the equilibrium. Calculation of equilibrium constant we are going to see. Here the problem is given. The problem is like this. Calculate the equilibrium constant for the reaction. We have given a reaction. And CO. We have asked to calculate the equilibrium constant for this reaction. So that means we have asked to calculate Kp. Alright. At 1395 Kelvin, if the equilibrium constant at 1395 for the following reaction are the equilibrium constant for these reactions are given. K1 is equal to 2.1 into 10 to the power minus 13. And another reaction is given, twice of CO2, which gives twice of CO plus oxygen. This all are again in a gaseous form. And the equilibrium constant for this reaction given is 1.4 into 10 to the power minus 12. So this is what is the problem. Here this is minus 12. Now, how to calculate therefore the equilibrium constant for this reaction? Now, see Kp here, if you want to calculate Kp, what is the equation for that? Now all these are in a gaseous form, therefore partial pressure of water into partial pressure of carbon monoxide divided by partial pressure of hydrogen into partial pressure of CO2. We want to know all these quantities, then and then only we can calculate Kp. But here no partial pressure of any of the gas is given, but we have given these two reactions, and from these two reactions we are asked to calculate the equilibrium constant for this reaction. See now, here what the species are present? Water and carbon monoxide, and on this hand hydrogen and carbon dioxide. Now therefore what we can do of these two, so that we can get these type of the products and the reactant. See, what can I do is, if I do K2 by K1, now K2, what will be K2? K2 will be, let's first write the equilibrium constant and then take their dividation. K2 for this reaction is equal to partial pressure of carbon monoxide raised to 2 into partial pressure of oxygen divided by partial pressure of carbon dioxide raised to 2. This is K2. Now what is K1? K1 is nothing but partial pressure of hydrogen raised to 2 into partial pressure of oxygen divided by partial pressure of water raised to 2. Now I am going to take K2 by K1. So here only I am taking K2 by K1. I am just substituting K1 here. Pressure of H2 raised to 2 into pressure of oxygen divided by pressure of raised to this raised to 2. Now what we are going to do is the same terms which are present here, that we are going to cancel. See therefore, have we no, none of the term is same, all are different terms, so no cancellation will be there. Let's what do therefore, let's just sum of them, calculate them. See, pressure of CO bracket into pressure of CO2 or oxygen, it is K2 CO. Okay, this is just O2. Okay. Now if you take it here, this will be inverted, right? If we try to write it in a multiplication, so the denominator go to the numerator and this will be the denominator. So pressure of water raised to 2 divided by, actually one term we forget to cancel, only one term is common and that is this term, and this term can get cancelled, right? Therefore this term is vital, only the two terms are left. See, this we can write as, if you are not understanding, I will tell you in a detail. And this denominator you can write it as inverse, as partial pressure of water divided by partial pressure of hydrogen raised to 2 into partial pressure of oxygen. So these two terms will get cancelled. Alright. Now pressure of carbon monoxide raised to 2 into pressure of water, partial pressure of water raised to 2, and the remaining terms here. Wait a minute. This raised to 2 into partial pressure of hydrogen again raised to 2. Alright. This I have told you in a detail की हे जे काही आपण लिहिले याचं आपण इन्व्हर्ट करताना इन्व्हर्ट असं होईल आणि त्याच्यामुळे हा जो काही ऑक्सिजनच्या सेम टर्म आहे तेवढ्या फक्त कॅन्सल झाल्या, बाकीच्या टर्म आपण जशीच्या तशा लिहून घेतल्या. आता पहा, आता हे जे काही इक्वेशन आले याच्याशी कंपेअर करा. हे पहा, याचा स्क्वेअर आलाय, याचा पण स्क्वेअर आलाय, याचा पण स्क्वेअर आलाय आणि याचा पण स्क्वेअर आलाय. याचा अर्थ I can write this as Kp square. करेक्ट? म्हणजे K2 by K1 करून जे ह्या ज्या काही टर्म्स आल्या, या टर्म्स Kp चं हे जे इक्वेशन आहे याचा जर स्क्वेअर केला तर एक्झॅक्टली असं इक्वेशन येईल. सो देअरफॉर K2/K1 इज इक्वल टू Kp स्क्वेअर. म्हणजे थोडक्यात आपल्याला असं इक्वेशन मिळालं, K2/K1 इज इक्वल टू Kp स्क्वेअर. आणि मग आपल्याला जर Kp काढायचं असेल, आपल्याला K2 माहिती आहे, आपल्याला K1 माहिती आहे. लेट्स सबस्टिट्यूट इट. K2 इज 1.4 into 10 to the power minus 12 divided by 2.1 into 10 to the power minus 13. This is equal to, आता हे जे काही येईल याला फक्त जर मला Kp काढायचं असेल तर याचा फक्त काय करावं लागेल, स्क्वेअर रूट घ्यावं लागेल. सो 1.4 into 10 to the power minus 12 divided by 2.1 into 10 to the power minus 13, and this is equal to 2.58. So this is the value of equilibrium constant here. आता इथे आपल्याला ह्या रिॲक्शन दिलेल्या होत्या आणि त्याच्यावरून आपण या रिॲक्शन साठीचा इक्विलिब्रियम कॉन्स्टंट काढला. काही वेळा आपल्याला यांचे कॉन्सन्ट्रेशन दिलेले असतील. मग आपल्याला जर कॉन्सन्ट्रेशन किंवा पार्शियल प्रेशर दिलेले असतील तर ऑब्व्हियसली डायरेक्ट या इक्वेशन मध्ये सबस्टिट्यूट करून आपल्याला Kp काढता येईल. द इक्विलिब्रियम कॉन्सन्ट्रेशन और पार्शियल प्रेशर आर गिवन. जर तुमचे लिक्विड फॉर्म मध्ये जर तुमचे रिएक्टंट प्रोडक्ट असतील तर त्यांचे कॉन्सन्ट्रेशन दिलेले असतील मोल्स पर लिटर मध्ये, आणि मग ते मोल्स पर लिटर मध्ये दिलेले कॉन्सन्ट्रेशन या ठिकाणी आपण सबस्टिट्यूट केले की आपल्याला इक्विलिब्रियम कॉन्स्टंट मिळेल. आता ही गॅशियस रिॲक्शन आहे. मग गॅशियस रिॲक्शन मध्ये यांचे जर पार्शियल प्रेशर्स दिलेले असतील तर ते डायरेक्टली सबस्टिट्यूट करून या पद्धतीने आपल्याला इक्विलिब्रियम कॉन्स्टंट काढता येतील. किंवा या अशा प्रकारच्या काही रिॲक्शन की ज्यांच्यात येणारे हे जे काही पार्शियल प्रेशरच्या टर्म होत्या या बरोबर या इक्वेशन मध्ये येणाऱ्या पार्शियल प्रेशरच्या टर्म फक्त त्यांचा स्क्वेअर झाला. त्याच्यामुळे K2/K1 इज इक्वल टू Kp स्क्वेअर असं इक्वेशन आपल्याला मिळालं आणि त्याच्यावरून आपण इक्विलिब्रियम कॉन्स्टंट काढला. नेक्स्ट टाइम वी सी द नेक्स्ट टॉपिक.